going to talk about this question in quite some detail. In fact, the solutions simply give an answer to part one, and that is it. They don't really give any insight into where it comes from. So I guess you can just try things out until it works. But I decided to try something out, and when it didn't work, go into a little bit more depth. Let me show you what I did. So I decided, right, I'm just going to label it 1, 2, 3, 4, 5, 6. Why not? And then for my edges, I'm going to get 3, 5, 7, 9. All good so far. 8. But then I get 7 again. And remember, they have to all differ, basically. So this doesn't work. So I didn't actually carry it on. You can do, you can just adjust it slightly and maybe you get there. But I'm going to show you how I then kind of got to an answer which had a bit more insight into where it came from. So I know there's 9 edges. You can count them. And 1 plus 2 is going to be the smallest possible total. And then 5 plus 6 is going to be 11, the largest possible total. Now, there are actually 9 numbers from 3 to 11, including 3 and 11. You can do 11 minus 3 plus 1, which gives 9. And so we have to obtain 3 to 11 as our edges. Because it's not possible to get 12, it's not possible to get 2. If we don't obtain them all, we're going to be repeating one of them, basically. Now, at this point, I decided to give it a go and see if I could get a possible answer, but just adjusting what I did at the start. So I went with 1 and 2. This time I decided to swap them around, so 5 and 6. So now this gives 6, 3, 7, 8, 11. All good so far. But let's take a look at this number here. If I put 4 here, then I'm going to get another 6. So I don't want to do that. If I put 3 here, then I'll be okay. But then when I put 4 here, I'm going to get 7. Basically, because I have to put 3 and 4 in still, I'm definitely going to get 7. So that is still not working. And then I decided, okay, I'm gonna now look at how I can get all these different totals. So here it goes. I made a table, a bit like a sample space diagram if you've ever seen one of them. So I've got the numbers from 1 to 6 and down here as well. Okay, I can't actually have them next to each other, so I'm going to cross all of these out. 3 and 3, 4 and 4, 5 and 5, and 6 and 6. And then I'm just going to look at the left-hand triangle because then I've included every possibility, in fact. Okay, and then add up this, because this actually shows straight away the only way I'm going to get my 3 is if the 1 and the 2 have to be next to each other. That's what this is giving. So there's one way to obtain 10 and 11 and one way to get 3 and 4. So 1 must be next to 2. And 3 to get us the 3 and the 4. 6 must be next to 5 and 4. So with that in mind, we can see why the other ones failed, because 1 was next to 2 here, but not 3. And here again, it was next to 2, but not 3. So let's try for the third time, see if we can work it out. But see what I mean by having a bit more insight now. So might as well still stick one here, but I'm going to put 2 here and then 3 here. Now, I need 6 to be next to 5 and 4. Let's just work out what we've got so far. We've got 4, 3, and 5. So if I put 6 here, that'll take me to 9 and 8. I now need to avoid, I could either put 5 or 4 here. Okay, but there's a problem now because then I'll definitely get 9. So I can't have 6 next to 3 if 4 is next to 5. But okay, that's given me a little bit more insight. What if right, I keep putting 1 in the corner, but what if I put 1 here instead? And then maybe 2 here and 3 here. So now I've got 4, 5, and 3. Brilliant. Okay, I'll get my 7 by putting 6 here. So I've got 8 and 7. And then it's just 5 and 4 remaining. Now I don't want to put 4 down here because then I would get another 5. So if I put 5 here and 4 here, then I get 10 and 9. Oh, and 6 here. So through 4 attempts, but increasing my knowledge basically through this little diagram and thinking about this fact here, I've managed to show that it is possible. And this is just one way. There will be others as well. Yes, it is possible. Now, in truth, when I did the problem, I actually did one other thing. I started to try and investigate whether it was impossible. Because it is a lot, well, in some ways it's harder to show that something is impossible. To show it's possible, we just need to find a solution. To show it's impossible, we could check every single configuration, but there's going to be a lot. So normally it's like a quicker way to do it. So what I did is I decided, right, I'm just going to label it A, B, C, D, E, F. Now, when I add my edges together, I'm going to get an A plus B from here and an A plus D from here. But overall, you can see that I'm going to get a 2A because there are 2 edges that join it. And then for B, I'm going to get 4B because there's 4 edges that join it. 3C, 3D, 4E, and 2F. So that's going to be my sum overall. Now I know I'm using the numbers from 3 to 11 and I'm going to add them all up. A quick way of doing this is to add up from 1 to 11, which is a half times 11 times 12. There's a formula, a half n plus 1, to add the numbers from 1 to n. I do recommend, well, reading about this, but also learning it and using it in situations like this, because I'm going to get 66, and I just need to minus a 1 and minus a 2, so it's going to be 63. Of course, you can do it the long way, but it really comes into its own for larger sums, and it's, it is just a quick summation method. Okay, so 63. All right, is this really that useful? Well, we also know that A plus B plus C plus D plus E plus F is 1 to 6. A half times 6 times 7, or 21. So if I take this sum, then I've got 3 lots of A plus B plus C plus D. Just playing with the sums really to see if anything comes out of it. And then I'm going to have to minus an A because actually I've got 2A here. I'm going to have to add a B because I've got an extra B. I'm going to minus an F and add an E. And that is equal to 63. Okay, let me just backtrack and just make sure you're with me on this. So I've basically added up every single edge. I've just, for this one I get A plus B and so on. And so I'm going to get A plus D here. And so I've realized I can just add up all the edges by adding up the number or how many A's how many edges are there. So I'm going to add up 2A's, 4B's, and so on. So I wrote that down. I used the fact that they've got to be 3 to 11 inclusive, worked out that was 63. I then just manipulated the left-hand side to write it so it's 3 times all of them added together, because I know that this is 1 plus 2 up to 6 in some order, and I know that sums to 21. So finally, and then I had to minus A plus B minus F plus E to make it all work out. So then I've got 63 minus A plus B minus F plus E equals 63. These are going to cancel. And what I've found out is that B plus E must equal A plus F. They must be the same for me to have a solution. So basically, the middle two here must equal, I think it was A plus F, must equal these here. Okay, and that it doesn't rule out a possibility, by the way, which at the time made me think, okay, now I need to just need to try some numbers out. So when I did it, I did also kind of think about this configuration. You can see now why this one works well. Well, it does. It has to be that these two add to these two, and you can see why it must fail for the other ones then. So as long as we get that to be the case, as well as the other conditions we have, are going to be pretty much there. So I suppose as soon as I made that 1, 2, and 3, I just had to find a pair here and here to give that property of getting 7. So basically, this information over time has just given us certain conditions and helped us to get the answer. Now, I know I've talked about this for a long time, but what it does also is give some insights into part 2. So, I didn't talk about it originally because I just thought, okay, we can get there with the solution once we've done a bit more digging, a bit more investigating. But now for part 2, we need to take it a step further and, you know, investigate whether this is possible or why it's not possible. So looking at part 2, personally, I was quite suspicious. I thought it's probably not going to be possible. Just the fact that the first one was possible, I could have been wrong, but that was actually my starting point. I think I've gained this information from part 1. Let's just go straight into it because I did have trouble getting the solution to begin with. So let's label it A, B, C, D, E, F. Right, now in the same sort of way, there's 9 edges. And so we know that's going to add to 63, just like before. But this time, I've got 2A plus 4B plus 4C plus 2D plus 4E plus 2F. When I add the edges together, this one being, say, E plus F, and this one being F plus C. So you can see where the 2F comes from. I've just kind of done it really quickly. So that must equal 63. Now I'm going to do exactly the same method. I'm going to say that I've got 3 lots of A plus B up to F. But now I need to minus an A minus a D minus an F, and then add on a B, C, and an E. And that is going to equal 63. This is again 21. So this cancels with this, and it must be that A plus D plus F is equal to B plus C plus E. But the problem with this is that A plus B up to F is equal to 21. And what this means is that this is not possible. If you're not quite happy why it's not possible, then consider this. If I take this and add B, C, and E to the left-hand side, then this would actually equal 2 lots of B plus C plus E on the right-hand side. I'm saying I'm adding B plus C plus E to both sides because this here is equal to 21. And I've just shown that this, well, is an even number. So I'm saying an even number is an odd number. So there's a contradiction. Okay, nice. So part one, we found a solution. I went into a lot of detail on gaining insight into it. Using that insight allowed me to do part two quite quickly, showing that in fact it is not possible to have every edge different using the numbers 1 to 6 on the little circles or the vertices. Whew, well done.